An important and powerful proof technique is known as proof by contradiction. And the way proof by contradiction works is as follows. Suppose I want to prove that P is true. Okay, some statement, all the integers satisfy something. Suppose I want to prove that result. And suppose that I assume that P is false, but somehow I reach a contradiction. Okay, so suppose that if I assume P is false, from there I conclude some sort of contradiction, or I get to a statement that is always false. If I get to a contradiction, then my assumption that P is false has to be false. Therefore, that allows me to conclude that P is true. This is really how proof by contradiction works. Now, usually where the contradiction that we know what P is. We're trying to prove that P is true. So that's given in the question itself. The question is that where do we come with the contradiction? That's, in some cases, it's clear from the question itself. And in some cases, it's actually tricky, and you have to think about it to be able to find, okay, what contradiction would make sense here? Because, x greater than 10 and at the same time x greater than -1 is a contradiction. But the question is, does that help in establishing the proof? That's not necessarily the case. So we have to find a contradiction that actually works for the proof, and that contradiction usually or always has to follow from the assumption that P is false. Okay, so let's see some examples of that. So suppose I want to prove that if 3n plus 2 is odd, then n is odd. Okay, so here what is it that I'm trying to prove? That 3n plus 2 is odd, that this implies this. Okay, so this is PQ, that I'm trying to prove that P implies Q. Remember that P implies Q is the same as not P or Q. Okay, and if I want to look at the negation of this, if I want to assume the negation of this, not P implies Q, the negation of this is by De Morgan's law, it's P and not Q. So if I want to prove this by contradiction, I want to assume the negation of this statement that I'm trying to prove, or it's P and Q. So I assume that 3 plus n, assume 3n plus 2 is odd, and n is even. Okay, so assume this. This is again equivalent. 3n plus 2 is odd, and n is even. This is the negation of what we are trying to prove. So if 3n plus 2 is odd and n is even, then again n equals some 2k for some integer k. Right? So if n is 2k, then 3n plus 2 is 3 times 2k plus 2, which is 6k plus 2, which is 2 times 3k plus 1. But this number here is even. So now we have reached a contradiction. What is the contradiction? Notice that we assumed that, I'm going to actually color it by red here. We assume 3n plus 2 is odd. We also reached that 3n plus 2 is even. So we have established 3n plus 2 is odd and 3n plus 2 is even. This is impossible, right? I mean, this is a contradiction. This whole thing is false. So if this is false, then the assumption that what we were trying to prove is false is incorrect. Therefore, we conclude from this that if 3n plus 2 is odd, then n is odd. Okay? So again, I was trying to establish this results that 3n plus 2 is odd implies n plus odd. I said, let me assume this is false. Assuming it is false is the same as saying assume 3n plus 2 is odd and n is even. When I did that, I actually, from this assumption, I managed to get to the point that 3n plus 2 is even. So I assumed 3n plus 2 is odd. I reached the conclusion that 3n plus 2 is even. This is a contradiction. Therefore, my assumption that 3n plus 2 is odd and n is even is false. Then, therefore, the negation of this must be true, but the negation of this is what we tried to prove, which is 3n plus 2 is odd, implies n is odd. Okay. Let's show now another example that's a textbook example of proof by contradiction. Prove that the square root of 2 is irrational. A number is rational. Number is rational is if you can write it as p divided by q, for p and q being integers. Of course, q cannot be 0. Okay? So 1/2 is rational, 1/3 is rational, 2 divided by million is rational, 5 is rational, and so on. Now, what we are saying here is that 2, the square root of 2, is not rational. What we are saying is that you cannot find two integers such that if you divide them one by the other, you will get the square root is being rational. Okay? So how do we prove this by contradiction? If I want to prove it by contradiction, I say assume that the square root of 2 is rational, right? So this is the negation of what what I want to establish. So if I want to show that the square root of 2 is irrational, okay, I say let's assume it is rational, and we will reach a contradiction. What does it mean to assume a square root of 2 is rational? From this means that square root of 2 equals p divided by q for some pq integers. Okay? Now, I will make an important statement here that later we will see why it is important. And please notice that I am making it because I know how to establish this proof. This should not be taken as when one tries to do this proof for the first time, this is what comes to mind. Okay, so again, a proof, you improve your ability to do proofs with more and more practice. So I will assume, without loss of generality, that not only PQ are integers, but I will assume also that the greatest common divisor of P and Q is 1. Okay? Assume that square root of 2 is P divided by Q, and greatest common divisor of P and Q is 1. What is the greatest common divisor? It's the largest number that you can divide both numbers by. So if you look at 2 and 4, their greatest common divisor is 2. It's the largest number that you can divide them both by 2 without remainder. What's the greatest common divisor of 9 and 2? It is 1. The largest number that you can divide 9 by and 2 by, and you get no remainder, is 1. Right? I cannot divide them both by 2. 9 divided by 2, I don't have a whole number. So why can I make this assumption? What if one wants P and Q to not have GCD being 1? Well, if you give me two numbers whose GCD is greater than 1, I can keep dividing them both until I get to that. So suppose you say, no, P and Q, their GCD is 3. Well, if their GCD is 3, then divide both of them by 3. Then you will get to two numbers whose GCD is 1, right? So I can make this assumption without changing the problem I'm trying to work on, okay? So let's now continue, and we will see why I made this assumption of GCD of PQ is 1. So if square root of 2 is P divided by Q, then let me raise both sides to the power to power 2. So then I get 2 equal P squared. Okay, or from this I can get that P squared is 2Q squared. Now, if P squared is 2Q squared, what we are saying is P squared is even. P squared is even. This means that P is even as well. Where is this? Again, we showed that if P squared is odd, then P is odd. Okay, or if P is odd, then P squared is odd. So P is even, then P is 2K for some K. Then I can write this as 2K squared equal 2q squared. From this, I can get 4k squared, 2q squared, and then I can get 2k squared equal q squared. From this, I get that q squared is even, and therefore q is even. And let me say it is 2 times L, okay? So q squared is even, therefore q is even. But now look what happened. P is even, it's 2 times k. Q is even, it's 2 times some other number L. But what's the GCD of these two numbers? What's the GCD of P and Q? For sure it is greater than or equal to 2 because both of them are divisible by 2. I can divide P by 2, I get K. Q by 2, I get L. Therefore, the GCD is greater or equal to 2. Now, look at these two statements. Look at the conjunction of these two statements. One says that GCD of PQ is greater than or equal to 2. One says the GCD of PQ is 1. So I'm saying certain number is greater than or equal to 2, and that number is equal to 1. How is that possible? The conjunction of these two is a contradiction. Therefore, that assumption is false. Therefore, square root of 2 is irrational. Okay? So this is how we establish the proof of this by contradiction. And again, if we didn't make the assumption that GCD of PQ is 1, and then we got, for example, suppose we got everything else right, then we would have got into the statement that GCD of PQ greater than or equal to 2. That doesn't contradict anything else. It does not contradict the assumption that P and Q are integers. For this to become a contradiction, we had to assume that GCD of PQ is 1. Again, the GCD, greatest common divisor here. So this is again a textbook example of proofs by contradiction.